their lunch or their nap after their lunch. Always obvious. So believe it or not, 7th week, right? It's going to get kind of busy for a bit. You've got a lab that you're working on now. I'll talk about that for a little bit. You've got a new homework assignment coming out today. And you have another lab a week from today. So the end of the quarter is going to be a little bit busy. But I want to talk some about the lab write-ups too, so that you don't overexert yourselves on those in particular. So anyway, lecture today is mostly about fast imaging topics. I've said it sort of many and several times and in different ways that MR is kind of a slow imaging modality, right? So I want to talk about some strategies today whereby we can scan faster or at least more efficiently. And we'll have another lecture later in the very end of the quarter on so-called parallel imaging and even sensing methods, which are even faster ways to scan. So this is just a reminder that we have another lab next Tuesday, and all I did was switch the early group and the late group, so figuring that's probably the most fair thing to do. But if in doing so that creates a conflict, then just let me know. Okay? Just shoot me an email, otherwise we'll stick with the same groups and so forth. This lab, I appreciate your patience with the last lab. That we hadn't done that lab before, we hadn't run it that way before with the Phantom and the case-based reconstruction and everything, so there were some hiccups, but I think everyone's got enough data to sort of work from. So I'll talk about the lab write-ups in just a second. But those are the groups for the next lab. You'll also get homework 3 back today. The scores were uniformly pretty good. So you can see what the mean and the standard deviation and the high and the low is, and then the class average for sort of total points so far. And I think it's a total of 45, I think there's 45 total points plus a bonus point. So it's but keep that in mind, and again, get your regrades in if you haven't done that already. There's only a few people that were sort of considering that option, I think, but let's get that done. 2 weeks, and you don't need one. What's that? Yeah. We can talk about it. We can talk about it after class. Okay, so that's just a little bit of nuts and bolts for the class. And then the class kind of, things in terms of lectures kind of wind down a little bit, right? Because we'll have some invited lectures for the last 2 weeks. So you focus a little more on your last homework assignment, which is going to, as a long due date, so you get it today, and it's not due until the end of 10th week. Right? So you have weeks to kind of work on it, so that should be able to manage the workload a little bit. That doesn't mean to start it late, and then try to figure it out later. I would definitely kind of pick away at it as you go. It's a good assignment, but it's a little bit, there's some tricky parts to it, I think. So start early would be my suggestion. Okay, so maybe quickly back to the write-ups for the lab. So people have been asking, so yes, 2 pages. And that means absolutely everything fits on 2 pages, right? And there's several reasons I ask you to do that, but that's just good scientific writing, right? Like you have to kind of squeeze in the most important parts. And 2 pages is actually a ton of space, right? We sometimes have to summarize, year-long projects in 250 words, right? So you'll be fine. Definitely include some images. You were asked to look at 4 different examples, so 4 different conditions. And by that, I just mean that there were at least 4 different experiments that you did where you rotated the object, or you changed the resolution, or you had a different phantom, and already those 3 things would give you several possibilities. When it comes to simulating, you just have to come up with an object in MATLAB. Just a binary object is fine, 0s and 1s. That's a pretty close mimic of the thing that you were actually imaging. So it's either a cross pattern or it's like a banding pattern, right? But pay attention to the resolution. The resolution of the object that you generate should be pretty close to the resolution that you at least imaging with or something like that. So that'll matter a little bit in terms of what you see in the Fourier case-based representation. So you're going to simulate some things. You're going to show me the magnitude for the image. You're going to show me the magnitude for the case-space. And you'll do that for 4 conditions. And you'll have that for your simulations, and you'll have that for the lab result itself. And the idea is just kind of comparing, right? You have the sort of perfect result that comes from your simulations, and then you have what you got in the lab. Lab wasn't perfect for several reasons. And just make some simple observations about what are the differences and sort of why do you see those differences. And that, everything that I just described there is probably, the bulk of the lab. That's a page or even a page plus of the lab. The introduction, methods, kinds of things can be pretty short. Your results is based on the sort of simulation and observations, and then your discussion is a chance to say something about what you observed. grade these pretty easily, I'll tell you that ahead of time. So these are mostly meant to be just a learning experience mostly. So focus on getting something. Okay? Okay. So if you came a little bit late, then these are just the lab assignments for next Tuesdays. And that was the homework score for the last one. And I'll give that out at the end of this end of lecture. You can remind me of that. All right, so learning objectives for the previous lecture. We'll kind of run through these a little bit quickly. You should be able now to describe the origin and the correction for several artifacts. So in the last lecture in particular, we probably went through 6 or 7 or maybe 8 different artifacts. And you should be able to kind of identify those artifacts based on the things that we talked about, and then maybe even talk about, not maybe, but you should be able to talk about solutions or ways to sort of mitigate those artifacts for most of what we talked about. You should understand the impact of spatial resolution and scan time on signal-to-noise ratio. So we had a really simple expression. Does anyone remember what our SNR expression was? We said SNR was proportional to V root T, right? So your spatial resolution affects the what we call voxel volume and pixel volume, and then your scan time, if there was an SNR, was dependent on the square root of scan time. So you have to scan for 4 times as long to double your signal-to-noise. We then spent some time talking about the importance of the readout bandwidth and the pluses and minuses of a high or a low readout bandwidth. So what's an advantage of having a high readout bandwidth? What's that? The bandwidth and the resolution are not related to each other. The readout resolution. The bandwidth it can change the TE a little bit, and that might change the TR a little bit, but it doesn't have too much of an effect on scan time per se. There was two main things it was related to. It followed after our discussion of signal-to-noise.
Low SNR and
yeah.
high resolution.
So let's talk about the first thing first. So for high bandwidth, you tend to have lower signal-to-noise. There's different ways to sort of think about that, but one way to think about it is high bandwidth meant you were moving across k-space very quickly. And if you're moving across k-space quickly, you don't get any sort of averaging. You're not getting hundreds or thousands of cycles of precession. You're getting fewer cycles of precession. So that was part of the 1. So high bandwidth means lower signal-to-noise. But again, effectively, within the constraints of our hardware, we can have any spatial resolution for high or low bandwidths. So there's not a direct effect on spatial resolution. They're not unrelated, but because of the hardware, but in general, they're so noise, and there was another one, chemical shift, right? So if you have high readout bandwidth, what effect does that have on your chemical shift? It decreases the chemical shift effect. So we'll talk about chemical shift actually a little bit more today, and it's going to come up in your next homework assignment. But with high readout bandwidths, you had less chemical shift artifacts. So these, we showed axial images of the head and the sort of subcutaneous fat like shifting or not shifting. So there's an advantage to go to low readout bandwidths, right? If you have a low readout bandwidth, then that's going to increase your signal-to-noise, but it's also going to increase the chemical shift artifact, and so you'll have more shifting of fat relative to water, and that's generally going to be a bad thing. Yep.
High readout bandwidth means strong gradient.
It does mean it means it also means a large gradient during the readout duration. Yeah, and so that's one way to understand why I say a higher bandwidth means you're moving through k-space more quickly, because k-space depends on the integral of the gradient time, or the gradient as a function of time. And if that amplitude is high, then you're going to integrate more quickly and move across k-space more quickly. Yeah?
Why the bandwidth is related to the magnitude of the gradient? It's just related to the envelope function of the RF pulse.
So the RF pulse is later. So this is readout bandwidth. So this is during acquisition, when you're acquiring data. The RF bandwidth is the excitation bandwidth, right? So we excite with a certain bandwidth, and that gives us, we're exciting a certain range of frequencies, but that's during the excitation process. And then once we've prepared our magnetization, at a later time, we're going to read it out in the form of an echo, and And there's different ways to sample the magnetization at the time at which we're measuring it. And that's related to the bandwidth. The bandwidth is really it's the delta time. We talked about this too. It's the delta time step that you use for sampling that echo signal, that temporal echo signal. And how much time you spend sampling it is also related to the maximum gradient. Shall we?
Is without bandwidth equivalent to the magnitude of the gradient?
Not equivalent to, but related to.
I guess it's gradient over 1.
Yeah, it's always hard for me to remember every sort of formula here, but higher bandwidth is higher gradient strength, so there's a linear proportionality between them. I forget everything that's in the right-hand side. Okay, so this is actually partly related to sort of the first one here, but defining the origin, artifact, and possible correction for chemical shift artifacts. So we talked about this in part already, with how we can modulate the bandwidth to affect the chemical shift artifact. So its origin is the fact that fat, for example, has a different resonance frequency than water. It's chemically shifted. The artifacts that you see is usually a spatial misregistration, and one possible correction for chemical shift artifacts is related to the bandwidth. And I'll show you another correction today, which is a useful thing as well. But if you have fat and you have water and you tip them down, they have different precessional frequencies, and so they won't always be in phase with one another. So there's times when fat and water are out of phase, and there's times when fat and water are in phase, and that creates some interesting image features that we'll actually talk about today. There was some good discussion about this after class, and we talked about this in class too, but how motion causes image artifacts. And the basic principle was that it takes you a finite amount of time to travel across K-space, from say the top of K-space to the bottom of K-space. And if there's motion while someone, if the patient is moving or an organ is moving while you're acquiring K-space, then you're basically blurring in different ways the object that you were trying to image, because the object itself was in different physical positions during the acquisition itself. And so we had different kinds of artifacts that we could see there. We looked at motion artifacts, kind of bulk motion artifacts, more like breathing, if you will. And then we also saw pulsatile artifacts, so how that would appear if you have, say, a vessel that's flowing with blood, and that gave a slightly different looking artifact. Conceptually similar, but slightly different. And we'll talk some about some of this chemical shift stuff today, and also some motion artifact related things as well. And then the last thing that we did at the very end of class is I gave you a single image with lots of artifacts, and you guys were able to pick out 5 different artifacts from that single image.
Excuse me, is the motion corrupted image in the spatial domain, the temporal average of the image in the temporal domain? Because in K-space, a kind of average, right? Because linear image space and K-space, the linear relation.
Yeah, so say your question again is?
So whether in the image space, the motion corrupted image is kind of temporal average image of the motion state.
Yeah, I mean it's a kind of average, but it's not exactly a linear average, right? It depends on the amount of motion that was happening during any, say, chunk or segment of K-space, but it's a kind of average for sure. And so we showed you some examples where, like in the pulsatile artifact, I shouldn't be putting this hands, I should write the slides, but with the pulsatile artifact, you had all of the static tissue still was acquired in K-space correctly and formed an image, but then you have this pulsatile artifact, and whether the signal was bright or dark depended on some physiology, right? And then whether the K-space lines were bright or dark depended on whether or not that signal was high or low as a function of physiology. So they were effectively separable things, the static stuff and the moving things, and then there is some kind of averaging effect. Okay. These are the things that we're going to talk about today, mostly the learning objectives, and then we'll come back to these at the very end, or at the very beginning, rather, of the next lecture. So we've talked about gradient echoes a fair bit, and we've talked about the fact that fat is off resonance. And I want to show you some practical aspects of this, and then this next kind of 10 or 15 slides, whatever, ties in relatively directly to your next homework assignment. So if you want to doze off, do that and wait 10 minutes at least. Okay. So you've seen different examples of this already. So this is just saying if you have a constant B0 field, then we expect all the water spins in a uniform field just to process with the same identical Larmor frequency. If we turn on a magnetic field gradient, then we expect to have a linear range in frequencies, low frequencies to intermediate, all the way up to high frequencies. And then, of course, in the presence of fat, fat is downfield. It has a negative frequency offset relative to water. And so in the presence of a gradient, fat may precess similar to one of its neighbors. So it's upfield because of the gradient, but it's downfield because it's chemically shifted. And so they end up appearing physically to have an origin that looks to be the same spatial position, and then there's a signal void where the fat would have been, because there's no spins reporting from that spatial position. So we've seen this in a couple different examples. And so these are just knee images. We looked at head images before. The readout direction is is up-down, and so we have a low bandwidth image and we have a high bandwidth image. In the low bandwidth image, you can see some signal pile up and sort of overlap here, and then below that you can see some signal void where this sort of fatty tissue is shifted away from. And then the higher bandwidth image here, you can see that it's more spatially well registered. There's not sort of obvious signal overlap, if you will. So we have the pile up and the lack of pile up. You have the voids. And then the other thing you'll notice too is that we have higher signal to noise and then lower signal to noise. So when our bandwidth went up, we expected that we were moving across k-space more quickly, and as one consequence is that the images themselves tend to be a little bit noisier. So there's trade-offs in terms of overall image quality. So this we talked about before. I should mention, if I didn't already, that with higher bandwidth, you can also slightly shorten up your TE. Right? So if you're moving across k-space more quickly, you can form your echo with a little bit less amount of time needed, and consequently your TE can be shorter, and then if you wanted to keep the same or similar image contrast, you might shorten up your TE. And then low bandwidth just has so in principle, there's two kinds of chemical shift. One's called type 1, and type 1 is the chemical shift artifact we've mostly been talking about, which is this spatial misregistration. Things don't appear exactly where they're supposed to, and clinically, does that matter? It depends. You might be able to read through it, or it might be really distracting. And then I'll talk some today on some quantitative techniques where it becomes problematic in particular. So in general, pixels are frequently a mixture of fat and water, right? So any pixel of any size, it's unlikely to have. It's possible, at least, that it's partly watery tissues and partly fatty tissues. So it could be entirely fat, it could be entirely water, but some mixture, right? The actual pixel intensity is the vector sum of what's happening to fat and water. So fat and water are in phase, they're going to add up together. And if they're out of phase, they can effectively cancel each other. So look at it this way. This is a pixel that's, say, half fat and half water, right? And those two spins are precessing around, but at slightly different frequencies, right? But there will be a time point at which they're back in phase with one another, right? If I wait the right amount of time, everything's whipping around at the Larmor frequency, but this is the Larmor frequency minus some chemical shift frequency. So just going back again, sorry, just to show you, they're going to be precessing, but at slightly different frequencies. There will be a time point at which they come back in phase with one another. Am I going to have a large signal amplitude or a low signal amplitude if that corresponds to my echo time? Large, right? Those two things are summing together. So my echo time actually plays a role in how these two signals combine. Right? I can control my echo time. I can freely select the time at which I want to form my echo. And if I wait the right amount of time to form my echo, then my fat and water can be in phase. And so adding together two vectors that point in the same direction, that's going to give you some vector sum that's, of course, greater than 0. You have some bulk observable transverse magnetization. If I continue to let them precess, I can get to a time point where, in fact, they're opposed. Right? So fat's out of phase with water. And you effectively get destructive interference, right? So the sum of some opposite-oriented transverse magnetization vectors gives me some zero sum. And so the TE is really important to the time. The TE is really important to sort of how fat and water contribute to the signal within a voxel. Now, it actually doesn't matter. Let's say if I doubled my spatial resolution, right? So that I had an entirely fat voxel and an entirely water voxel. Would my TE dictate my signal magnitude anymore? No. So spatial resolution actually plays a role in this as well, right? If I have higher and higher and higher spatial resolution, then it's less likely I'll have pixels that are partially fat and partially fundamentally, it depends a little bit more on the time itself, the echo time. So what can we do with that? Well, okay, so the TE controls the phase between fat and water, right? And so this is something that you can plot out for yourself. If you know the off-resonance frequency for something, so let's say we're talking about fat, and it's about 220 hertz. It depends exactly sort of on what you read or what you cite or what you measure, but fat's off-resonant by about 220 or 225 hertz. And so the period, meaning the time at which fat and water will be in phase with one another, happens at about 2.2 milliseconds, and then it happens again at 6.8, and then, it happens at 4.5 milliseconds. They're in phase with one another. There's no phase difference. There's zero phase for fat relative to water. I get that happening first at about 2.2 milliseconds, and then they process around, and they come back into phase again with one another at about 6 milliseconds, 11 milliseconds, and then, pointing to the wrong things. That happens at 4.5 milliseconds, 9 milliseconds, 13, 18. So you can control your echo time such that the phase from fat is basically zero relative to water, and that would have fat and water in phase with one another. I can also control my echo time so that things were totally out of phase, and if they're totally out of phase, then I'm at where these like dashed lines are, right? So it happens first at 2.2 milliseconds, then it happens again at 6.7 milliseconds. So what's the consequence of that? This is where we saw. So here we can see that the TE is going to control the phase between fat and water. We actually pick the TE. We don't usually pick how in phase or out of phase things are, except in that we control the echo time itself. So here's two images. All imaging parameters are held the same. The bandwidth is the same. The flip angle is the same. The TE, the TR. The TR is the same. The TE you have to make small modifications to. And so here we can see the in-phase echo time. That means fat and water are in phase, and everywhere inside this image, if they're partial voluming within a pixel, then they're going to coherently add together. Whereas if they're opposed phase, as shown on the right-hand side here, then you start getting these sort of streaking artifacts that stand out a little bit more distinctly, kind of some darker bands and parts of the muscle, and especially, say, at the edges of what we expect to be fat and what we expect to be muscle. You'll typically get these darker artifacts here. And so that's precisely where you have a pixel that's something like half water and half fat. They become, in the opposed phase image here, or out of phase image, then they destructively interfere. So it can be useful diagnostically to control the phase of the signal, or the phase of the fat and water signals, so you can see and identify differently sort of fat from nearby watery tissues and fat from otherwise other bright tissues, if you will. So this is an example of what we call type 2 chemical shift, and it's also sometimes called the Indian ink artifact. But when your images have these sort of darker bands and arguably at boundaries or maybe in slightly unexpected areas, that's maybe not the best example, but here, that's an indication of the so-called type 2 chemical shift artifact. So here we can just do a little test, right? So we have two images here. One's the in-phase image and one's the out-of-phase image. So who wants to vote for? We're trying to figure out which is the in-phase image. So raise your hand if you think A is the in-phase image.
We could depend on the sequence, right?
We'll talk about that in a second. But the sequence is controlled. So right now it doesn't depend on the sequence. So who thinks this is the in-phase image? About half of you. I'm guessing about a third of you vote. Who thinks the B is the in-phase image? Okay. So what are you noticing?
I think there's more dark region, like hazy egg region. It's different regions.
So there's more darker regions here. Right. So is darker regions in phase or out of phase?
Oh, I mean it's all phase, but
yeah.
I also noticed some dark region in the first.
Yeah. It's really confusing. Welcome to MR, where nothing is perfect, right? Yeah. So let's think just about the in-phase condition, right? So in-phase is fat and water pointing together, right? And there's different regions I could point to, but let's look at the tongue, right? So this is a head and cross section. Probably figured that out. This is the spinal cord and the spinal column. So this is someone's tongue in cross section, right? And just compare the tongue here to the tongue that you see over here, right? So now what do you think?
The horizontally.
Yeah. And so this is the in-phase image. You can see some intralingual fat in the middle of the tongue, and then on this side here, when that fat is out of phase or opposed phase with the surrounding water, then you get the sort of lower water fat. And there are other. It's not to say there's no dark regions in this area or in this image. You have to know or understand something about the tissues and expected tissue signal intensities to maybe see it very easily. But yeah, so at any rate, the left-hand side is the in-phase image. Different regions that we can point to sort of identify. Okay, so there are reasons why we might want to do fat suppression. Oh, actually, well, I'll come back to your question in a second about sequences, right? I think, Xiaohuan, you were asking about like gradient echo or spin echo, maybe?
Yes.
Yeah.
Yes, like spin echo is water fat issue.
What do you think? Well, it depends on what you mean by issue. So is it an issue? Yes, everything's an issue. So let's try, so we can be more specific, right? So the artifact that we're talking mostly about right now is when fat and water are in phase or opposed phase, right? So what happens to things that are off resonance in a spin echo image? What's that, buddy? Yep. So that refocusing pulse will offset many and several different sources of off resonance. Chemical shift is one, but susceptibility or B0 inhomogeneity, like lots of sources of off resonance. But that 180 pulse will shift over in the first half of the echo, fat and water will be coming out of phase, but then you're going to flip everything over and they're going to come back into phase, just like all the off resonance spins. So the spin echo sequence doesn't have this same inherent artifact. Okay, so gradient echoes, they're actually really nice sequences for being fast. We typically have kind of short TEs and TRs, and they're also that's good for T1 weighted imaging in particular. So why would we want something like fat suppression or separation? Why would we want to get rid of the fat signal? Lots of reasons. In particular, fat is bright on most pulse sequences, and fat's not usually that interesting, meaning it's not generally pathologic, right? Now that's not entirely true. There's plenty of studies that are looking at fat now increasingly, fat in the liver, fat in overall in your body, distributions of fat in your body to understand sort of different morbidities associated with that. But for lots of things, say cancers, for example, fat itself may not be the interesting diagnostic thing to look for. And yet it's bright on lots of images, so maybe it'd be nice just to be able to knock out the fat signal if you knew how. Lots of things are bright, right? CSF and edema can be bright, flowing blood, contrast-enhanced tissues. So anytime you can sort of knock down one signal and say, oh, well, we knocked down fat, that might give you more insight to what's happening for that particular imaging exam. So it could, in fact, sort of obscure some underlying pathology, whatever it is. So how can we eliminate fat? Well, there's a bunch of different ways, actually. You'll see this in your homework assignment, and we'll talk about a couple different ways here. But you can use so-called fat saturation pulses. So you can actually saturate the fat signal so it doesn't come back at the time you're forming an image itself. Interestingly, you can also do what we call water excitation. So you can excite only water and ignore fat. And the basic principles, again, there rely on the fact that fat resonates at a different frequency than water. And that all assumes that fat does exactly one thing and water does exactly one thing, and that usually requires that your magnet is perfect and there's no inhomogeneities and these kinds of things. So everything can, of course, get a little bit trickier. So we'll talk a little bit about fat saturation pulses, and we'll also talk about multi-echo acquisitions. You already know that fat and water don't always have the same phase, right? And so there must be a trick, right, where I could get multiple images with slightly different phases and learn something about the presence, absence of fat based on their different phase behavior. So we'll look at that. This is one example of fat saturation, the pulse sequence that you could use for this. And so we'll look at it at the beginning here. This is a preparation pulse, right? And so you have a 90-degree pulse here, and it's highlighted just to be gray in this case here, because the center frequency for that pulse is centered on fat rather than water. So it's just 220 hertz off, or maybe 440 hertz off, but it's such that it will excite fat, and ideally fat only, right? You can have this narrow bandwidth RF pulse that excites just fat. And as soon as you excite it with a 90, you tip it over, and then you spoil it. So that means any fat magnetization that you had, you were able to tip just the fat down. Water was unaffected. You tipped it down, and then you spoiled it. So you spread it all out in the transverse plane, and it ideally won't contribute subsequently, right? And then you just start off with, in this case, a gradient echo acquisition. So you play your alpha pulse here called a theta pulse, slice selective, do some phase encoding, and do a readout to acquire an echo, and then spoil again, and just repeat the process. But the real point here is that you can, because of its frequency sort of uniqueness, you can excite fat, spoil it, and then it won't contribute when you acquire your subsequent echo. So little tricks. And there's a bunch of different tricks, and you're going to see some of this already, but in your last videos. One of the problems, though, with fat-sat, the approach, for example, that we just talked about, is that it can be spatially non-uniform, right? So you're relying on the fact that this RF pulse here will only act on fat, and that's not exactly going to be the case, right? It's not fat-specific; it's frequency-specific. So then you're left to, you know, how perfect is your field? How perfect is the frequency of fat for a particular subject? And so images like this are not uncommon, where you're trying to suppress the signal from fat, and you expect to have, for example, subcutaneous fat, say, running down the neck and back here, and some of the fat's not suppressed at all, and some of the fat's suppressed pretty well. This is a relatively extreme example, but it's a suitable example to show that it can be non-uniform.
Is it an issue of zero equationarity?
Not just B0 inhomogeneity, but, well, yeah, so B0 inhomogeneity, that's because of B0 itself, like maybe the field that you have in your magnet is not especially good, but then the subjects themselves can also perturb the field, right, for even further. You can shim, right, you can always try to tune the field to be more perfect on a patient-specific basis, but even that's not going to be perfect. And the frequency shift between fat and water is also small, right, so this is a difficult sort of problem, so to speak. Okay, so it works. We can do that. One thing that's nice about it is it's an extra RF pulse, so it doesn't really change the length of your pulse sequence by very much. It's just one little trick that we can throw in. What's another option? Well, another option is to actually separate out fat and water. How do we do that? Well, here's a gradient echo sequence, right? You should recognize slice selection, phase encoding, and then your readout gradient, which helps you form this gradient echo at this point in time table. Now, depending on the exact timing, I don't know why the arrow's going way over there. I should just end here. So for TE1, you'll have some phase between fat and water, right? Whatever that TE is will dictate the phase between fat and water. We can, in fact, turn this gradient over and acquire a second gradient, or a second echo, right? So this is reading out an echo, say, from left to right. This is called a multi-echo sequence. We can turn on a gradient negatively and actually come back across k-space and form a second echo. That second echo will be a little bit lower in amplitude because there's, of course, been some T2 star decay, and it'll form at a different echo time, but that's okay. It just means that fat and water have slightly different phase relationship, and that's actually useful to us because now we're getting some information about how much phase is accruing between these two things in the imaging. And then we can do it one more time. We can turn on another positive gradient in this sense here, and then form a third echo. It'll have a slightly lower amplitude because it's got T2 star waiting on it. That signal is decaying from the time point at which it was excited. But again, the main difference between these different signals that we can acquire is the amount of phase, the angle between fat and water is going to evolve as a function of the echo time itself. And then you can actually set up a least squares problem. There's several different formulations to actually solve for how much fat and how much water there is in a particular voxel, if you will. We're not going to go into, there's many and several ways to do this. I think one of the later guest lectures will talk about this in part. But from these different measurements here, we can do a fat-water reconstruction and actually separate a water image and a fat image. So you can reconstruct the water-only image and the fat-only image, if you will. So what does that look like? Well, it looks a little bit more like this. So these images are similar. That's the same subject as to what we saw before with the in-phase and opposed-phase images. But now on the left-hand side, we're ideally forming just a water image. And that means all the spins here were on resonance and had the right phase relationship such that they produced signal absent of any underlying fat signal. And then interestingly, on the right-hand side here, you get a very, sort of fat-only like image. And so it's very dark in areas that you would expect, still in the airway, for example. But it's also very dark in a lot of the watery tissues, so the brain tissues and the spinal column and so forth, that you expect to be very watery. And it's very bright in regions of subcutaneous fat, in the intervertebral discs. This is anterior fat that's subcutaneous, and then you've got some fat in the chin and tongue and things like this. So a really pretty powerful technique for separating out and making a water-only image and a fat-only image. So this is just that comparison of the different possibilities of getting the imperfect fat sat, the water-only, the fat image, and then the in-phase, the fluid phase. These I don't think are probably used quite as widely as they anymore in the clinical sense, and increasingly with just acquiring a few extra echoes, which might extend your acquisition time by a bit. You can actually separate out water and fat, and in fact, you can even make that a quantitative measure and start talking about the percent of fat inside of that pixel, for example. Okay, so questions about sort of chemical shift in fat and water? Like I said, you'll see a little bit more of that in some simulation.
So to clarify, a few slides ago when you showed us the graph of the frequencies, it kind of looked like, yeah,
Yeah, we're getting there.
Right.
Right. It's coming. It's going great. It's the problem with losing.
yeah, that one, yeah. So these TE values, these are like manually inputted TE values, correct, that we set?
When you're on the scanner, you can pick your TE, yes.
Okay.
What you don't pick is how fat and water relate to one another, because that's just through the off-resonance frequency,
Okay,
right?
perfect.
So you have an off-resonance frequency F. This is something like 220 hertz or 400 hertz at 1.5 or 3T, and now we can define the period, right? So just 1 over the frequency. And so what's happening at the very beginning when your TE is 0, then of course fat and water are in phase, right? So the phase of fat is 0 relative to water. But as the TE evolves, then the fat is drifting away further and further and further from water. And so it's going higher, it's having more and more amounts of phase until it gets up to pi phase. And when it gets to pi phase, then it just wraps down to minus pi phase. And it's going this way now. And when you get all the way out to an echo time of like 4.5, you've gone all the way around to being out of phase at minus pi, and then you come back around again to being in phase. And so the first time fat and water are in phase is at 0, and then they're in phase again at 4.5.
Okay, so here we set the TE time to 2.27.
You could. If you set the TE time to 2.27, fat and water will be out of phase.
Oh, okay, so this is just the general graph for how fat and water
Yeah,
interact.
this is just the phase of fat relative to water. And it increases, but because it's only on plus minus pi, then it wraps. And
Okay.
anytime it crosses 0, that means the phase of fat is 0 relative to water.
Okay,
I probably could have gotten that through that more clearly.
Alright, perfect, thank you.
Yeah?
I have one question about this method, because during the whole readout gradient, we are acquiring the data, right?
Yep.
But only at the time of TE, at the peak of the echo, we can get this in phase, but during the other time, it will not in phase.
No, that's right. That's absolutely right. And so, we can't use the 0 echo time in general. So let's say we got to the echo time of 4.5 milliseconds, right? What you're saying is you're actually acquiring data starting about here through the middle of k-space when your echo forms, and then a little bit further as well. And that's exactly right. And that means that in principle, your fat and water they're never in phase during the entire readout. They're just in phase, say, at the middle of the readout, right? And so that will have an effect, meaning they're going to be out of phase in some negative sense before the echo forms, and then out of phase in some positive sense after the echo forms. Nothing we can do.
So it's not perfect.
It's not. Nothing's perfect. We should have Joe.
The water image and the fat image you show, are they purely proton density weighted?
Well, there's different ways to reconstruct that. So they don't have to be purely proton density weighted.
Because if it's not proton density weighted, the signal intensity information not only telling you about the fat
Yeah, no, you want it. I mean, you want it to be as proton density weighted as possible, right? So you, because the proton densities of fat and water aren't that different, right? So then there's no signal magnitude when you're trying to figure out from, say, the signal intensity what the mixture is. You want the contribution from fat and water to be very, very similar, right? So how do you form a proton density weighted gradient echo image? What kinds of TE and TR do you need? Do you remember? Short what?
Short T.
Yeah, short TE, long TR, right? That would be the ideal circumstances. Now, it turns out you can model all of this as well, right? So you can build more complicated models that, maybe assume something about the T1 of fat, or assume something about the T1 of the tissue, and then you can separate out the magnitude and phase contributions, both of which actually matter. Yep. Okay, so let me just pop ahead here a little faster. Okay, so the sort of last sort of 2/3 of this lecture or whatever is primarily about ways to image faster, right? So we've really only talked about full K-space acquisitions, filling up all of K-space, and that's the requirement for then doing a 2D-FT and forming an image. But it's not actually a strict requirement, and there are so-called partial Fourier imaging strategies. So this is one technique for fast imaging. And the basic idea is that you could do different things in terms of acquiring partial or fractional amount of K-space. On the left-hand side, it's actually a trade name, partial NEX. NEX just means averages. So this is a so-called partial average. I could acquire all of K-space twice. In this case, I've only gotten maybe 3/4 of K-space. So this is one possibility. I could go through K-space. I could have a large phasing cogradient take me out to the edge, and then I could step through K-space all the way down to, say, the middle here and not get those lower lines of K-space. We'll explain what that means or conceptually does to your images in just a second. That's a possibility, right? The other possibility is what's shown on the right-hand side, which is what we usually call partial or fractional echo. And that just means that when you're playing your gradients, you don't have to come all the way out to this point in K-space. You can just come part way out and then read across. Your echo would still form here, and you can keep reading out, or you can keep reading out, and you can keep going, right? So these are two different strategies for so-called partial echo acquisitions. So the first question is, how do you acquire each data set? So what does it mean to acquire this data set? This answer is a little bit easier, right? You just don't have to go through all of the phasing code steps. We said originally you'd have to go through 128 steps. Well, you don't. You just go through 96 of those steps, for example. On the right-hand side, I alluded to it a second ago, but you just don't have the readout pre-phaser doesn't have to be as long, right? You're not going to pre-phase all the way out to here. You're just going to do partial pre-phasing and then turn on your gradient, read to the middle of K-space, form your echo, and continue reading. So it's all about how many phasing code steps you choose to acquire, and then how much pre-phasing you choose to do. What's an advantage or disadvantage of each approach? Well, let's think of it together. What do you think is an advantage of this approach here? Short time, right? So the whole point I said was that this would be faster imaging approaches, right? Why is it faster? You don't have to get these phasing code steps, right? So if this takes you a second and a half, you don't have to get this last half second of data, for example. So fine, it's faster. Right-hand side's another possibility. What do you think is the advantage of that strategy? How much shorter is it? I still have to go through apparently all my phasing code steps. So it may not have even changed my TR, right? It should change my TE, right? So my TE is shorter because I didn't have to pre-phase as much, and then I don't have to read out for as long. So I can, instead of having to come all the way out here and all the way back, my TE could be quite a bit shorter. What's good about having a shorter TE? Signal to noise, right? Less T2 star decay. So this strategy here, it'll shorten up my TE. If I shorten up my TE, I can shorten up my TR a little bit, but it probably doesn't help my acquisition time very much. What it mostly is going to do is have an effect on my signal to noise, less T2 star decay. So what do we know about K-space? If you've looked at it carefully, you've probably noticed this in some of the examples that we've been showing, but there's always this sort of symmetry. Usually in the middle of K-space, it sort of has this almost cross pattern through the middle of K-space. You can sort of see it in the background here. And that's because for a real valued object, the K-space itself will in fact have a specific symmetry that we call Hermitian symmetry. So if your image, the thing that you're imaging is actually real value, that means it doesn't have any sort of, it's not complex value, then its frequency representation, which is the S of K's that we acquire, it's actually redundant, right? So when you do the 2D-FT, there's redundant information in there, if you will. If S of K is known for all of our K points that are, say, greater than 0, say the top half of K-space, then S of K for the bottom half, K less than 0, can be generated just according to this idea here, which is the notion that our K-space is Hermitian, or what we call conjugate symmetric. And so I'll show you what this sort of means or sort of graphically in just a second, but if you have the signal at some minus K position, then you can produce the signal at another location from the data that you actually did measure. What does that look like? Well, it looks something like this, right? On the bottom left-hand here, I'm saying this is some K point that I particularly care about. I can generate a synthetic version of this data point and put it up in here. So had I not acquired this data point, this Hermitian conjugate data point would be the best substitution I could make. And that's just mathematical. It's the fact that the 2D Fourier, if your object is real valued, then your K-space will have a 2D Hermitian symmetry. So what that actually means is that you could get away in principle with just acquiring, say, the top half of K-space, and then every point in the top half of K-space is Hermitian symmetric with some other point in the bottom half of K-space. So in principle, that's possible. There's pluses and minuses to those partial Fourier acquisitions. In general, every point in K-space that we acquire has both magnitude and phase. We usually just look at the magnitude information, those kind of K-space figures that I keep showing you, but there is some phase information that goes with those as well. And the phase of the signal at any K point may not be the same as the phase of the signal acquired at its sort of Hermitian conjugate K point. So there can be some differences in the actual phase I would get for these two different points of data. Why are there differences? Well, a simple one is noise, right? I get those two K points, those two Hermitian symmetric K points. When I acquire that K point there, if I acquire all of K space, I won't get an identical value for this K point here. They'll be different at least because of noise. And if they're different because of noise, I don't actually know which the right one is. I just know that there's two possibilities, right? Well, there's other reasons that that K point that you measure might be different between those two Hermitian pairs. You can have motion during the image acquisition. There could be some resonance frequency offsets, like during the acquisition. There are hardware problems and delays that happen during the acquisition, things like eddy currents, coil phases. There's all kinds of imperfections that mean those two K points won't necessarily be identical, even if we expect them to from the object being real value in the first place. So what does it mean? Well, there's still some advantages, right? We talked about most of these already. In the readout direction, you can reduce the echo time, which will improve your signal to noise because you have less T2 star decay. It'll also reduce what we call gradient moments. We haven't talked about gradient moments yet. It'll come back in the flow lectures. But gradient moments are integrals of our gradient waveforms multiplied by time. So there's, just like statistical moments, there are several gradient moments. And they give us sensitivity to flowing spins or moving spins. But you can tighten up that as well. In the phase encode direction, we said this already, it ultimately should reduce your scan time. So that's a plus in terms of scanning faster. Of course, there's disadvantages, right? So anytime you're scanning faster, you have to be doing something to, well, decrease your signal to noise. There's different ways to reconstruct it. We're talking about going back and only acquiring, say, the top 3/4 of K-space, right? If I do so, what do I do with the bottom K-space that I have here? Well, the simplest option is just to fill it with zeros, just so-called zero padding. We talked about that some for sort of getting synthetic resolution out of your imaging data. Oops. So you could just do that. That will actually result in some blurring of your images. So these partial Fourier approaches have some inherent blurring associated with them. We won't get into the details, but there are some more complex reconstruction algorithms that are pretty commonly used. They're going to increase the reconstruction time a little bit, but that's relatively trivial anymore. And they'll still have some blurring related artifacts. But you can, in fact, do very good imaging with just these partial Fourier approaches. Yeah, so that is an option, right? So okay, first option, zero padding, right? Simple, but we'll have artifacts. Second option would be to take that K point and just put it in down here. You can do that. You will get some, especially at the back where where the acquired K space meets the not acquired K space. You usually have a little bit of a discontinuity because there's differences in the K space you would have acquired from what you actually acquired, and that discontinuity will give you artifacts in your images as well. And so this so-called homodyne and Plox reconstruction techniques are ways of trying to sort of smooth out those problems. Okay, so maybe, yeah, why don't we take a little bit of a break, and then we'll come back and we'll talk about a few other sort of just high-level ways of scanning faster, and then I'll get you back going. Okay, so like 5 minutes? 2 minutes?
Up to you.
What's that?
Up to you.
That's up to me. You want to keep going? We'll take a couple minutes break and then we'll come back. The rest of the lecture won't take all that long.
算它有分 free electron 和不 free electron， 但是那个还有更多的问题。你能找到那一块吗？就是讲那个的，讲那个就是可以看那个地方。
因为我记得，
我记得，对，我们懂为什么要做这个问题。
后来我发现，你说这个是对的。
那我就想，那可能跟你说那个就不是同一回事。我就是这个找到。Really? What? I'm just rolling my leg, super tight and working out. Just walk. How'd you hurt yourself? Oh, you're actually really good. Just rubbing it against the cheek.
说不的情况下是说你这东西踢完之后，你看它是没有到别人的情况，你再通过不是别人说的话，你踢的。
Oh yeah, because you can see how it's like.
最好是正负嘛。
She's like low-key disturbed. You said to sit down and do your midterm anyway. It might be. When did you finish it? Yeah.
他想到这个位置，给他的数目这个写。
Oh, and now you can do it.
这个正好差点拉。
It was. I've read really good things about it. I actually am not a fan of it.
是，我这样看的话，
Yeah, though there's so many.
最派 OK， 最派，
My friends were
就
very
像
good.
这样表达怎么派，
Yeah, I had to watch it.
所以说你派。
So you guys send me emails and have me do the list. I think what happened is
It's like Fear Factor.
what's like here?
This outdated show Sarah likes.
It's a really old show I still watch.
That's the beauty of like all things internet,
Yeah.
right? Like, when they come out, it's always
Oh yeah.
All right, guys, I'm gonna go ahead and get going. So this is kind of high-level concept stuff today, right? Without a lot of some of the details that we had in some of the other lectures. So I just want you to conceptually appreciate what some of the possibilities are here. So again, the theme here was really fast imaging, right? How can we image faster than we otherwise might, right? So here's an example of a spin echo sequence, right? 90, 180, phase encoding, 4-minute echo. But we may, in principle, have so-called wasted time, meaning there's time during which we're not doing anything. Why would that be the case? Why would I have wasted time there? Why wouldn't I just play my 90, say, for my next TR right away? What's the main reason? Okay, so I can get rid of the transverse magnetization. I didn't draw them, but I could put spoilers on, and my transverse could be gone in 500 milliseconds. So, a couple milliseconds. What's that? Why? Yes.
Well, I mean, otherwise you won't have anything to go for it.
Yeah, but sometimes that's okay. So I want to. There's one key word I'm trying to get to. What dictates how we choose our TR? Because we're trying to get a certain kind of what? Image contrast, right? And so what dictates when we play the next 90 is mostly, do you want T1 weighted? Do you want T2 weighted? What kind of contrast do you want? And for a spin echo sequence, I mean, this sequence of events on the front end here is milliseconds, right? Maybe it's 5 milliseconds, maybe it's 20 milliseconds. But the TRs that we oftentimes want in spin echo are hundreds or even thousands of milliseconds. So there's wasted time here. It's not really wasted. It's sort of like waiting for film to develop, right? You're waiting a certain amount of time so you can have the contrast that you actually want to have. But it doesn't mean you have to do nothing. And so one strategy here is actually to do something with that time. So imagine doing this. You excite, refocus, and acquire an echo for one slice, but then you just move down to another slice. Right? So I've excited, I've refocused, I got my echo. I'm just going to let this slice recover. And now I'm going to move down to this slice. And I'm going to excite it, refocus it, get my echo, let it recover while I go to the next slice, and then the next slice. So you can do so-called slice interleaving, right? And the advantage there is you're going, in some sense, 3 times faster. You're getting a little bit you're only getting one echo for these 3 slices, and then you have to repeat that process to get all of your echoes for all of your slices. But in the time it would have taken you to get slice 1, you've now gotten slices 1, 2, and 3. And by extension, you could squeeze in maybe 16 slices or 20 slices, depending on the specifics of your protocol. Okay. So what does that look like, sort of in terms of actual imaging time? Well, normally we do something very sequential, or everything we've discussed so far has been very sequential, right? We get a line of K-space, we get the next line of K-space, and every line that we add takes a full TR. So that means that our imaging time is our TR times the number of lines that we have to acquire times the number of slices that we actually want to acquire. We hardly ever just want one slice, right? We usually want full, head coverage or full chest coverage or the entire knee or whatever, right? Okay, so what's the alternative? It's the slice interleaving approach, right? And therein, for those 3 or 4 slices, you can zip right through and get different lines. Get a line for, say, every slice that you're interested in, and then at the second line, at the third line, until you're all the way done. And so now your imaging time still depends on your TR. It still depends on how many KY lines you need. It still depends on how many slices you want to acquire. But you can divide it by the so-called number of interleaves. How many slices have you interleaved into that single TR? So you easily get acceleration factors of 2, 4, 8, right? And that's significant in terms of total acquisition times. So simple, and a pretty good trick. What's the advantages? Well, obviously you can accelerate the imaging by, integer factors, which is significant. Disadvantages are you can only squeeze in so many interleaves, right? You'd have to extend your TR if you wanted to get even more interleaves, but that might actually be a good thing. Sometimes we choose our TRs to be a little short just for imaging speed, but maybe you can lengthen your TR even more for, say, T2 weighted imaging and get even more slices and have a overall more efficient protocol. The downside, though, is that there's only so many interleaves that you can squeeze in, so it's something like the TR divided by the TE, not exactly, but close. And then you could hit a SAR limit, right? Now all of a sudden you're playing a lot of 90s, a lot of 180s, and that might be too much energy deposition according to the scanner backbones and hardware limits. A more technical problem is that it's difficult to acquire immediately adjacent slices. So if you want to get this 4 millimeter slice, and then move down 4 millimeters and get the next 4 millimeter slice, and then move down and get the next 4 millimeter slice, that ends up not working so well. And the main reason for that is when you design your RF pulses, they have a slice profile. And the slice profile of your 180 pulse is not as narrow, typically as narrow and as refined as the slice profile for your 90-degree pulse. And so what does that mean? Well, you remember the sort of ripple artifact that we had, and then there was the sidebands? Those sidebands are really broad. They're exciting spins and adjacent slices. And so it's difficult to have the slice profiles for the 90 and the 180 match. So what do? Well, you might just get the odd slices interleaved, and then in a separate experiment get the even slices interleaved. You just need some distance between those slices to sort of mitigate that effect. What kinds of applications do you have for this sequence? Well, again, we need long TRs for T2 weighted imaging, right? In particular, we need long TRs for that. So this could be good for T2 weighted imaging. And diffusion weighted imaging is another good example. Oftentimes we have a TR that's relatively long for signal to noise purposes. Because DWI, which we haven't talked about but will, is a lower signal to noise acquisition method. Okay, so that's one possible trick. Another trick for scanning faster is so-called multi-echo spin-echo imaging. We've seen some multi-echo examples, so this won't be entirely unfamiliar. You know this expression or something similar for total scan time. TR, that's the number of phase encode lines times the number of averages that you might acquire. And so we know that we can pretty quickly get up to acquisition times that are many minutes, which is a lot just to get a single image, right? Lots of things can happen, patient motion and all kinds of things. But this assumes we're only getting one echo per TR, and that's not strictly required either. So here's a spin echo sequence. You've seen this before. The 90 to the 180 form an echo. Wait a bunch of time before we do it all again, and that's that wasted time. One possibility, though, is to add additional 180 pulses. And so now we play the 90 to 180 to form an echo. We can actually form another spin echo by just playing another refocusing pulse. The spins will sort of come out of phase, and then they'll be forced to rephase again through the application of another refocusing pulse. So you'll form an echo, a second echo at a later time, but it'll be of lower amplitude because there's still T2 decay from the initial excitation, the first 90 here. And then you can do it again. You can form a third echo, and in fact, you can form a fourth, a fifth, a sixth. And multi-echo sequences that acquire 16 echoes or 32 echoes are definitely achievable, and then there's some pluses or minuses as to why you might actually do that. One disadvantage, of course, is that these echoes are going to have some envelope on them, meaning that the first echo is going to be highest in amplitude, and the later echoes, the 16th or the 64th echo might be quite low in amplitude. And that means that there's some weighting across your K-space, right? If this is your first K line at the top of K-space, it's going to be inherently brighter than, say, the second, third, or 64th line of K-space.
Because we know, like, the T2 decay, can't you just try to modify the signal?
Yeah, you can. It turns out to be tricky, right? So the first problem is how well do you actually know the T2, right? So you may or may not. An even more difficult problem is that when you're getting the echo signal, the echo's coming from the whole slice, right? So it's not just dependent on like the T2 of that pixel. It is kind of eventually dependent on that, but this echo is the sort of integrated sum of the behavior of all of the pixels. So then you really have a problem.
But how do you weighting them?
Sorry?
But how do you weighting if you don't know the ratio between them?
You're asking me how to weight it? I'm saying it's you can't really.
So just increase.
So for the image reconstruction, how to
So you have an image of different.
Oh, hey, one question at a time. Really, so let's come back to your question. Do you want to try again? I don't know. That's all.
So for the image reconstruction, how to define the final amplitude for each case space?
Well,
We just use this value, or
so there's no value, right? Like
Yeah.
this just gives me a voltage in my coil,
yes,
right? And that voltage is going to be bigger here than it is here or way down there.
So
Right.
for the different position in the y space, ky, we have a different amplitude because the amplitude became more time.
That's right. Yeah.
We
And
just
so,
use that for
sorry, I'm just grabbing.
you must have some method to weight it.
Well, that's the problem though, right? So let's say this is k space, right? And so I'm going from this is ky plus, and then of course down here is like minus ky, right? So normally I'm getting these lines of k space, and maybe my trajectory takes me from top to bottom, right? So my acquisition strategy is going this way, times advancing along that axis, right? With this example here, it means that there's an envelope on this imaging data. That means I have to weight it something like this, and this is decaying according to something like T2. So this echo that I fill into k space here is very bright. By the time I get to the bottom here, it could be quite dark. Okay. The next question is, well, what does that do to my image? Right. That actually will effectively broaden your point spread function. Right. One way to think about that is these last high resolution points in k space will be very dark. It's almost as if you didn't acquire them. So there is some darkening of k-space as you traverse it this way, and that will effectively broaden your point spread function. If it doesn't make sense that it's essentially not acquiring these lines, then the other example is to say, well, there's no way it's going to sharpen the point spread function. There's nothing sharpens it, right? So does that answer your question?
So is there any method to just
So you won't
redefine
adjust.
this amplitude?
It's very difficult to make this adjustment because you don't know what this curve actually looks like. Right? We don't know the T2 of the object that we're imaging, and then even more problematic is the envelope, the actual T2 decay here doesn't depend on the T2 for the pixel, but for everything in that whole slice. So it's some kind of funny average, probably is kind of linear, of all the T2s in the entire slice. Because when I acquire an echo, that's an echo coming from the whole slice. There's tricks you can play. You could actually decide that, let's say this is line 1, this is line 32, and this is line 64. I can move my phasing code. I can kind of jump around in the phasing code ordering if I want to. There can be some problems with that, but these are you don't have to go top to bottom or bottom to top. You could jump around. And so if I wanted to, I could actually use the phasing code, say the 30-second phasing code first. And that would put the very first echo in the middle of k-space. And then I might get 31, and then I might get 33. Right? So I could jump, it's called a center out trajectory. Start in the middle and work my way out. And I could do that. And then I would be distributing this envelope of decay over all of k-space such that it would actually end up looking, it would sort of go from the middle out, right? So it would go like this. Does that make sense? So I would take the largest amplitude for my 30-second line would actually be physically happening. If that's not confusing. Sorry.
But here, are you assuming in one TR you can get the whole k-space?
That may or may not be a good assumption, but that's what I'm drawing. Yeah. But maybe again, there's so many possibilities here, and that's part of what I think makes MR interesting. There's all these various combinations where you could try things and then evaluate what really works. But you could choose just to get your even echoes or your even KY lines, and then repeat this and get your odd KY lines, something like that. It depends how many echoes you think you can acceptably get without totally compromising your image quality or something.
So the T2 decay will modify the image contrast.
it can modify the image contrast, and it can also modify the point spread function. Right? And so what I did by moving the first echoes to be the middle of k-space, right? That's going to have a strong impact on the image contrast. Right? I'm putting those first echoes in the middle. That's going to give you more T2 weighting in the middle. Yeah. Okay, so let's just carry forward and see some examples, right? So here's a spin echo image. On the right-hand side, you can see this is 2,500 milliseconds, right? 2.5 seconds. ETL stands for echo train length. So here, there's no echo train, not multiple echoes, just single echo. Next is averages, so just one average. And if I want to get 24 slices, this particular protocol to get 24 slices would take me about 22 minutes. That's a long protocol. You would never choose to use that protocol. So what's an alternative? Well, here's spin echo on the right-hand side versus a fast spin echo, so getting multiple echoes in a row. Keep the TR relatively constant. We can talk about the TE in a second. Here I'm using an echo train length of 16. So I'm doing one excitation and then 16 refocusing pulses. So I form 16 echoes in a row. And I'm choosing here, or actually Frank did this, I'm getting 2 averages. So I know if I accelerate by getting multiple echoes, I'm probably going to lose some signal to noise as well. Those last echoes aren't so great. So I get some signal to noise back by averaging. I still cover 24 slices, but my scan time now is just under 3 minutes compared to 22 minutes. Right? So this is a dramatic increase in sort of overall possible scan time. But there's some interesting artifacts too, or some interesting consequences. One thing you'll notice, and we'll talk about this a little bit, but look at the fat on the outside here. The fat's actually pretty bright, right, relative to fat on the spin echo image. And the spin echo images, when they're just like single echo, spin echo images, these are usually sort of the most true to contrast, images that you can get. Once you start throwing sort of tricks at these sequences, and they're so-called contrast deviations. Part of what happens, or we'll talk about in a second, but all of those refocusing pulses actually have an unusual effect on fat and make fat look a little bit brighter. And that's a sort of a spin physics effect. So, that's a lot of acceleration, right? You've effectively gone 16 times faster, but then we slowed it down a little bit with some averaging. So what's the downside? Well, here's echo train, say 4, so 4 echoes in a row versus 16 versus 24. You can go to these high echo train lengths to reduce your scan time, but it's going to ultimately introduce some blurring, some broadening of that point spread function, depending on sort of how extreme the effect is, or how short the T2s are, for that matter. So another interesting consequence is with these long echo train sequences, you actually have different point spread functions for different T2 species. Okay, that's really weird, right? So that means that really short T2 things in your object, in your image or whatever, they'll be blurriest, and really long T2 things won't be blurry, maybe at all, right? So now you have this really strange spatial resolution concept of being T2 dependent spatial resolution. That's not an obvious consequence. So what are advantages? Well, obviously the turbo factor, or the echo train length, is going to accelerate imaging, right? You're going 4 times or 16 times as fast. You can actually combine it with 2D slice interleaving too, right? Get multiple echoes on this slice and then move to the next slice and the next slice. So those techniques can be used together. And in fact, it's not an obvious problem, but T2 weighted imaging in a breath hold is tricky because you typically need really long TRs for T2 weighted imaging. So using some of these tricks like echo train lengths, multi-echo acquisitions can set it up so you can do that in a single breath hold. Disadvantages: once that turbo factor gets higher, you're going to get blurrier images, and you can in fact alter the underlying image contrast, so that's a problem. And then I pointed out on the images with the long echo train that the fat was really bright. So fat and watery light things should both be bright on the T2 weighted image, or generally kind of bright. Water and CSF, for example, they have a long T2, so they're going to be bright on the T2 weighted image. Fat has a shorter T2, but these repeated 180s actually reduce the spin-spin interaction. That's not obvious. It's a chemical shift effect. And it effectively lengthens the moderate T2 of fat. And so that means that even though this T2 is kind of intermediate, it can behave as if it's longer and more, say, CSF-like. So we saw, going back a few images, that the fat was actually brighter than just the conventional spin image. And then, of course, anytime you're playing more 180s, say, per unit time, then sorry. maybe one last fast sequence. This is sort of the gradient echo equivalent, or kind of a spin-in gradient echo equivalent. So it starts off the same, 90 and 180, to form, say, the first echo. But instead of playing 180 pulses after this, we play gradient refocusing pulses. So this is our readout gradient on the bottom here. We have this is effectively the negative readout pre-phasing gradient. It's positive because it's before the 180 pulse. So any phase from this is flipped over by the 180 pulse. And then we have the readout gradient here to form the first echo. And you can actually just play an equal and opposite negative gradient. If this first gradient is moving, you say positively across k-space, then you're just flipping around a second gradient to come back across k-space. But there was a little tiny phase encode blip here. So you actually moved up a line and then read back across k-space, and then moved up a line and moved back across k-space, and up a line and back across k-space. And so this is an example of getting maybe 8 echoes, but you're getting those echoes going left to right, and then the next echo is right to left, and then left to right, and right to left, for example. But those echoes will also T2 star decay. There's no refocusing pulses, so it's not T2 decay. It's pure T2 star decay. And any off resonance that you have will sort of be accumulating during all of those echoes. So not just the T2 star, but some off resonance problems as well. It's a pretty widely used sequence. I mean, you can see immediately that your acceleration again would be a factor of 8 or 16 or 32. And in fact, you can do so-called single-shot imaging with this approach. It's done frequently for what's called fMRI or functional MRI. A lot of neuroimaging groups use that. And so you may, in fact, actually carry the cyclotrain all the way up to 64 or 96 echoes, even though those last echoes are going to be kind of garbage. So you can get data in a single shot. It can be used in collaboration or combination with the 2D slice interleaving technique as well. So you could zip through all of k-space on this slice and then zip through all of it on this slice and so forth, and still keep a long TR for each of the individual slices. And in that case, you could get, say, T2 star with imaging. Disadvantages, there's lots actually. When you move through k-space that quickly, and there's the possibility for hardware imperfections and sources of off resonance and motion. You'll definitely typically see ghosting artifacts. You'll have the blurring of your underlying image information because of the same T2 star effect with weighting across k-space. You can get image distortions and also alterations to the actual image contrast again. Interestingly, you can do so-called multi-shot EPI. So multi-shot EPI would be a trajectory where you're moving through k-space to, say, get just maybe the odd lines, and then repeat it again and move through k-space and get the even lines. So that would be 2 shots. First shot for the even lines, second shot for the odd lines. But you can conceive of phase encode trajectories that take you through every 4th line, or 7th line, or 8th line. Lots of applications. Diffusion-weighted imaging in particular. This technique gets used a lot. Diffusion-weighted imaging we haven't talked about yet, but you, in principle, need to get many images to form the contrast that's of interest. And so fast imaging becomes especially important. Perfusion imaging is trying to image the perfusion of blood, usually during the passage of a contrast agent. And that's a very short time event. And you might want lots of images during this perfusion event, so fast imaging is really important. And then fMRI, we won't talk about it all in this class, but it's a way of looking at neuromodulation in response to behavior or stimuli, and it also requires really fast imaging approaches. Okay, so where are we for? Oh, this one's fine. Okay, so you have a lab on, well, let me back up. Questions about some of those 3 or 4 different sort of fast imaging approaches? Those are just qualitative. I'd like you to have some kind of qualitative insight as to what the pluses and minuses are to these approaches, but we're obviously not getting deeper into the mathematics of these approaches.
So why you have distortion?
Why? It can happen for different reasons, right? So if you go back to the EPI sequence here, right? In this example here, there's only one echo that is an actual spin echo, right? So you have the 90, the 180, and the first echo we're forming is this echo here. So that's going to be, you're going to acquire it quickly, and it's going to be free of off-resonance artifacts, right? Subsequent echoes will have an accumulation of more and more off-resonance. That can lead to blurring. You can also have, for example, so-called eddy currents, right? So there can be system imperfections that add that act as additional sources of off resonance to the echoes, effectively adding field shifts to the acquired echoes. And that means that when you're acquiring the echo, when you design your gradients, your intention is to get a very specific, say, line of K points. But if your gradients are in any way imperfect, the data you actually acquire will be somewhere else in K space. So let's take an example. This is again just say KY and KX. And this is the line of data that my gradients have, that I've designed, should have me acquired, right? Moving linearly from left to right in a very perfect and smooth line. If there's any imperfection in any of my gradient hardware, right, then the actual data I acquire may actually be something like that, right? Or it could just be something like that. So if there's a difference between what you actually acquired because the hardware is imperfect and what you intended to acquire, you'll have various kinds of artifacts, right? The point being that the K point you acquired, you don't know where it actually belongs in K space. And that'll give you artifacts that can look like ghosting artifacts or even like respiratory sort of motion artifacts. Why is that a problem in EPI in particular? Because those sources of off resonance are accumulating for all subsequent echoes. There's no way of getting rid of them. So if you have just the smallest field imperfection at the time of the first echo, a small field imperfection doesn't really do much. But that effect doubles for the next one, triples for the third echo, and could be 16 or 32 times as bad when you get towards the end. Other questions? No? Okay. So when you come to lab on Tuesday, what you're going to be given, you're going to have a little bit more sort of governance or whatever for actually running the scanners. TAs will still be there to sort of make sure things don't break. But you're going to have to give them instructions and sort of tell them what you would like to do. And the problem you're going to be faced with is a terrible protocol. Okay? So we're going to give you an object that you're supposed to be imaging. We're going to give you a really bad protocol. And you're going to have to spend some time, and we'll give you sort of a scoring system whereby you actually make changes to the sequence protocol until you get what you think is a good quality image. Okay? And then, assuming all three scanners work, you'll be competing against the other group that's on that same scanner for sort of image quality, right? So we make a little bit of a head-to-head. And so I'm going to walk you through at least one way of doing so-called protocol optimization. And the sort of governing principle here is how we would do this if we wanted to image faster. So some of the kind of concepts that we're talking about here will be relevant. It's not all of them, but some will be relevant to your lab that's on Tuesday as well. Okay, so we're going to start with what I call the infeasible protocol, right? So let's say we want to get a T1 weighted gradient echo image, right? That's our goal. The doctor says, T1 weighted image. You say fine. So we're going to just start some of these protocols. Some of these parameters are sort of just chosen, right? And so our TR is 162 with a 4 millisecond TE and 30-degree flip angle. That part I'm not going to change during this sort of example, if you will. And we start with this is actually a relatively big matrix size, so 256 by 256. And I start with a relatively big field of view, 480 by 480. Given my matrix size and my field of view, I can calculate my resolution. Right? Just one divided by the other. And so I'm currently, with this protocol, I'd be about 2 by 2 millimeters in plane resolution and maybe 8 millimeters thick. Okay? So that's all my sort of starting parameters for this sequence. Not every possible parameter, but the ones we really care about right now. And if I run this protocol, it's going to take me 43 seconds to acquire that data. Okay? So if I want to get a T1 weighted image using a gradient echo sequence, sometimes called flash sequence, and it's going to be in the abdomen, say, through the liver maybe, 43 seconds is a long time for most people to hold their breath, especially patients. Right? So we have a problem, right? Okay. Well, the scanner will give you a number. We talked about this before, the so-called relative signal to noise. Here, I'm scaling my relative signal to noise to say that for this particular protocol, my signal to noise is 3.4. It's arbitrary units. It's normalized to something that's 1. There's a protocol that we're going to get to where the signal to noise is 1. So the way you should understand this number right now is that my signal to noise is maybe higher than I need it to be. 1 is maybe a good sort of target. So I've got more signal to noise than I need, and that's possible. You might say, you know what, image quality is better than I need to make my call. I can handle lower image quality. It'd be much better if the protocol is shorter for the patients. And that'll probably give you better image quality anyway, right? So what happens with a 43-second breath hold? The biggest thing that you're going to be faced with is breathing motion, right? We talked about motion artifacts in the last lecture, but in 43 seconds, most people are going to end up breathing before the end of that 43 seconds. But one advantage of this particular protocol is we have a lot of signal to noise. Of course, the scan time is too long. And arguably, it's relatively low resolution. 2 by 2 millimeters is not really great imaging resolution by any standard. And this is what the actual acquisition would look like. So this is it's a T1 weighted image. I have a pretty big field of view, but I can see some respiratory artifacts here. I've got some blurring through the liver, right? This patient didn't hold their breath for 43 seconds, so things don't look so good, right? And by reference, this would be the case-based data that maybe I would have acquired, right? So the light box on the outside there is maybe like higher resolution case-based. So I said this image is kind of low resolution, so I'm just getting some kind of middle part of a possible case-based that I could acquire. So that's the setup for the problem, meaning I want to step through how we could optimize this protocol using different things we've learned about today and in the previous lectures to actually get a higher quality image. Questions about sort of what our starting point is? Sort of the assumptions. Because then we'll just kind of work through some different possibilities. So what else can we do? Well, first thing we might do is just decrease the field of view, right? Field of view is pretty big in this previous one here. What happens if I decrease my field of view left to right? Let's say, well, okay, question. If you looked at this image right now, can you tell me what's the readout direction and what's the phase encode direction? Okay, so you're pointing this way. Left, right is readout, right? That doesn't have to be, right? You saw it in the lab, hopefully last week. It could be either. So how do you know left, right is readout? Yeah, so not so much the aliasing, but you see the breathing artifacts, right? Or the respiratory motion artifact in this direction. That's a phase encoding artifact. So that's good. Right away, you know that frequency encoding is this way, phase encoding is this way. What happens if I reduce my field of view left to right? Any aliasing? Frequency encoding is left to right. Frequency encode direction doesn't alias because we oversample that signal when we're actually doing the digital sampling of the voltage signal. So I can't alias in this direction, but I can alias in this direction. Okay? So that's okay. I'm going to reduce my field of view. Can I handle reducing my field of view anterior, posterior direction? Totally, right? There's nothing here and there's nothing out there. So it should work fine. And in fact, it does, right? So we're going to reduce the field of view. What's in red is what I'm doing, right? So I'm reducing the field of view. The consequence is higher resolution. I've gone from 1.9 by 1.9 to 1.2 by 1.2. That's pretty good. I know it's going to hurt my signal to noise, because why? Okay, let me ask that a different way. Why is it going to hurt my signal to noise? My scan time didn't change, unfortunately. So it's still 43 seconds for this person to hold their breath. I did get more resolution. Voxel size, right? So my voxel size went down considerably, right? Because it was almost 2 by 2, and now it's almost 1 by 1. So it goes down by not quite a factor of 4, factor of 3. Okay, so I took an SNR hit, but I'm maybe still above 1, but it's still 43 seconds, so I'm still going to have some breathing motion. But I did get some higher signal to noise, and I will sort of focus my field of view, right? It'll be more focused on the patient itself. But unfortunately, my scan time is still too long. So what happened in everything, right? So this is my previous image, right? Just as a reminder, this is what we had a second ago. So my field of view is tight. That's pretty good. I chopped off their arms, but they don't mind, right? I could probably reduce it even further up down, but we'll get to that in just a second. But it's still 43 seconds, so you still see the motion artifact, right? You still see this really kind of blurry all throughout the abdomen, and then you can detect some distinct artifact outside of over here. On the left-hand side, it's showing what K points I need to acquire to get this actual image. What changed in K space relative to the previous protocol? Delta K, right? My field of view changed, so my delta K changed. So I went ultimately out to farther points in K space, because this is a higher resolution image after all. But my step size, what changed really was my step size. Not the number of points I'm acquiring, but my step size. Field of view got smaller, resolution went up, but matrix size actually stayed the same. Okay, so that's a step in the right direction, but it's still a long protocol, right? So one thing we can do is we can add what we call partial phase field of view. My field of view doesn't have to be square. You might have seen that in the lab last week. My field of view can be arbitrarily rectangular. Left-right rectangular or up-down rectangular. So here I'm going to change my matrix size. I'm going to reduce my number of phase encodes, but I'm also going to reduce the field of view in the phase encode direction. Okay? That means that as I've scaled it, I'll keep my resolution the same. But because I have fewer phase encode steps, right, I finally bring down my acquisition time. Okay? So that just means I'm getting less data, right? I'm getting a smaller field of view, less data. I can scan a little bit faster, but that will affect my signal to noise. My signal to noise has to come down a little bit. I have the potential for, aliasing artifacts if I'm not careful. And at 33 seconds, the patient probably still wants to breathe. So I've reduced the scan time. I've also reduced the signal to noise, and the scan time is still, I would say, too long. But this is the image that I could potentially get, right? So previously we had this kind of square field of view. Now I've reduced the overall field of view to be tighter, especially, say, across the anterior and posterior parts of the patient. And in terms of what happened in K-space, I just have an even bigger delta K now, right? My step size in the up-down direction has to be a little bit bigger so that I have an even smaller field of view. So getting there, right? Still not a great protocol, but getting there. So what else can we do? We can add partial Fourier, right? That'll let us scale faster. We learned today that there's redundant parts of K-space. I don't have to get all of K-space. So I could just get 3/4 of K-space. Still go through the same imaging protocol. Interestingly, when I get 3/4 partial Fourier, it means I'm going to get 3/4 the number of phase encode lines. So I should scan faster, but it won't change my resolution, right? Not in the sort of matrix sense. There might be a blurring artifact because of this missing K-space, but in the matrix sense, it doesn't change anything. So if I reduce the number of phase encode steps I need, then obviously I can push my acquisition time down even lower. And now I'm at what I call the relative signal to noise of 1. Kind of arbitrarily chosen, but this is my protocol where I say I have adequate signal to noise. There might be some subtle blurring because you did the partial Fourier approach, but now it's arguably breath holdable, right? A patient, that's long actually for patients, you guys would probably all be fine, but having patients do that multiple times can be taxing, and 23 seconds is still on the upper end of things. What's the disadvantage? Well, I've decreased the signal to noise, but maybe it's an acceptably good signal to noise. And so here's an example of what that image might look like. And now finally, things are starting to look pretty okay, meaning I don't have respiratory artifacts because they can hold their breath. I start to see some details in the liver here, right? These bright spots are actually vessels, larger vessels and then smaller vessels. And the overall image quality is decent. It's not blurred, it's relatively sharp, and it can be acquired in that 23-second scan time, for example. Okay, now what? Still 23 seconds. Like what tricks are still available to me? You can't really decrease the field of view anymore, right? If I could decrease the field of view left-right. Does that really help me much? Not really. It might tighten up my echo time a little bit, but it's not really going to help much. What happens if I decrease my field of view anterior-posterior? Aliasing, right? If I go much further, it gets too tight, and then all of a sudden I have aliasing, and that's a tough artifact to read through. I probably can't really increase the partial Fourier fraction. We didn't talk about this in real detail, but you typically have to get at least like 5/8 of K-space. And I think the example we chose was 3/4 or something like that. So you have to overscan, go past the middle of K-space at least a little bit. There's some reconstruction reasons for that, but we can't really decrease it too much more or increase the fraction very much. You could decrease the TR, right? We didn't do anything to specifically address TEs and TRs yet. That might, by decreasing the TR, you're probably going to lower your signal to noise, and you're also going to alter your image contrast. So that might not be a great choice, especially if the directive was for a T1 weighted image. We can play with bandwidth, right? We haven't addressed that at all yet. We could increase the bandwidth, so higher bandwidth, right? That means we're going to read across K-space more quickly, so that will allow us to shorten up our TE. And that could get us a little signal to noise, but it's higher bandwidth, so that takes our signal to noise down. Doesn't really affect the TR very much, and it's not great for signal to noise. You could decrease your spatial resolution, right? You could say, well, maybe this 1.2 by 1.2 is higher than I needed, and let's go ahead and go lower spatial resolution. But of course, that's going to blur the images. One possibility, though, would be asymmetric voxels, right? So we talked about this in the context of reconstruction 2 or 3 lectures ago. The data that we acquire doesn't have to be square pixels. They can be rectangular pixel data. There's nothing that limits us in that sense. So we could go through the same protocol, right? And in this case now, what I'm going to do is just acquire even fewer phase encode steps, right? I'm not going to go as far out in k-space for the phase encoding direction. So if I don't go out as far in k-space, then I have lower resolution. So you can see here that my matrix size is the same, the number of ky lines is down, and my resolution is increased, or the dimension of the voxel is increased. The good news is fewer phase encode lines mean I scan faster, so instead of 23 seconds, I'm down to kind of 19 seconds. That's a pretty good thing. And in fact, my signal to noise has actually gone up, because my pixels used to be square, and now they're rectangular. So the trade-off is sort of scan time is down, signal to noise is up, but my resolution is arguably a little bit blurrier. And so you have the so-called partial voluming effect, where you have these rectangular voxels rather than these square voxels. But you did decrease the scan time, but you have this. But this is an example of that image, right? So if you go back and look at the K data, we just take out 1 or 2 or some of the top K lines. So with lower resolution than the phase encode direction. This image, it's a little hard to tell because we don't have them right next to each other, but this is slightly blurrier in the up-down direction than the image that we had a little while ago. So whether or not that's a favorable trade-off is arguably sort of a clinical decision. You could go more asymmetric, right? So you can keep pushing this so that now we have pixels that are almost 1.2 by twice that, right? And you can really get the acquisition time down 12 seconds. That's pretty fast. But you're going to have even worse partial voluming blurring, even though you've decreased the scan time. And arguably, the signal to noise is maybe too high. Now, maybe you've overdone it, right? You've gone too far. And the spatial resolution is too low. And so here, you can maybe see it a little bit. This starts to look a little blurrier, right? The pixel size now is very rectangular, so to speak. And some of the details that we were able to see in the liver before, the smaller vessels are kind of blurred out and kind of washed out. The boundaries sort of between the fat and water in the back are kind of blurred out. Things just look a little more kind of fuzzed over. But it was short, right? All of a sudden, I'm down to 12 seconds compared to that, say, first protocol, which was 43 seconds. Okay, so here's that sort of head-to-head comparison, right? So this is isotropic or square resolution, so 1.2 by 1.2, versus anisotropic resolution, 1.2 by 2.3. So you could get this image in 23 seconds, or you could get this image in 12 seconds. And again, if you just look carefully, you'll see that there are features back here that are much sharper, much more detailed, more distinct than those same features in the image on the right. The signal to noise is arguably a little bit better here. So again, at some point, it's this sort of qualitative thing. What does the physician need to see? How well do they need to be able to see it? If you're a measurement scientist, then there's things that we can measure and sort of assert about the image quality of these two images. So this is where we would arguably end up, right? The infeasible protocol that really just was not well optimized, and then all the different steps that we could go through. But we could go too far, right? We could go down to low resolution images that are quick to acquire, but arguably not acceptable image quality. So I would say that this is not acceptable, nor is this acceptable, but something in the middle likely is. And so it's always about optimizing, right? One extreme is no good, the other extreme is no good. Something in the middle is going to be a better solution. So when you do this, in lab on Tuesday, you won't be imaging a person, unfortunately. You'll be imaging an object, and your first images will be way worse than this. So way worse. So it'll be fun. It'll be actually hard at first for you guys to figure out what's going on, but then that's the fun, right? Okay. So you can the minimum. You can minimize sort of the total K-space acquisition. Yeah, it's a funny sort of lead in there, but the point is that you can decrease your scan time in different ways, but you have to be mindful of your overall signal to noise, and especially other changes that could have happened in terms of image contrast, obviously the spatial resolution and the signal to noise. There's always these sort of trade-offs between what we acquire and, of course, the time numbers that we actually get. And you could, what we didn't talk about is throwing in some of the other tricks that we have, right? So how would a multi-echo acquisition sort of help this strategy? Or how would a multi-slice acquisition help if you were trying to get more than a single slice for the abdomen through the liver? Okay, so that wraps things up. That's a sort of long-winded example of how we actually go through optimizing these things. Ultimately, we've gone through that process, and those protocols just sit on the scanner. The downside is there's probably 1,000 protocols on the scanner, right? So then you still have to know a lot as to what protocol to use for what application. That wraps up the lecture. Questions about sort of what we're doing now or next? Yeah.
So in this example for the partial Fourier, we use the zero values, zero padding, we use the conjugate value diffuse missing.
In this example, I don't know what was used, to be honest, because I was just using the reconstruction on the scanner. So I don't know what their sort of favorite reconstruction strategy is for that. It's not zero padding, but I don't know what one they're using. Homodine, POX, and then there's others. Okay? Okay, thanks guys. I've got the homework, so I'll hand those back. If you have questions, Eric was the TA for this assignment. He's heading out for more job interviews tomorrow. So the solutions, I think, are on the website already, so you can look there first, and then you can always try to connect with him on email. He's going to be a little hard to touch base with for the next kind of week, except for over email. Phil? Sorry.
Thank you.
Yeah. And two. Oh my gosh. Last name Fu?
J.
I don't know. No name on it. Is that yours?
Oh yes.
Junjae? Junji? And Vahid? So I still have Junji Chen's. Are you going to see?